The Fourier transform generally decomposes a signal into a summation of sinusoids that, when added back together, construct the original time domain signal. The purpose of this is to analyze how much of a particular frequency is present in a signal. For example, if the Fourier decomposition yields that the time domain signal is the sum of a cosine at frequency 2 Hz and amplitude 5, as well as a cosine at a frequency of 10 Hz and amplitude 1, then you note that your signal contains the frequencies 2 and 10 Hz, with more of the 2 Hz than the 10 Hz. There are four main types of Fourier decompositions: the Fourier series, the continuous time Fourier transform, the discrete-time Fourier transform, and the discrete Fourier transform. The type of transform that you use depends on the time domain signal you want to analyze. The Fourier series operates on continuous periodic signals. The continuous time Fourier transform operates on continuous time aperiodic signals. The discrete time Fourier transform operates on discrete time aperiodic signals, and the discrete Fourier transform operates on discrete time periodic signals. In this tutorial, we will explore the discrete time Fourier transform. As I mentioned, the discrete time Fourier transform operates on discrete time aperiodic signals. Suppose that we take a time domain signal, let's call it x of t, and it can be anything. We'll make it continuous. This is our continuous signal. So to obtain a discrete signal, one common way to do that is through sampling. And we can define our sampled signal, let's call it x sub s of t, as x of t times an impulse train. In other words, a bunch of delta functions from negative infinity to infinity, which are each time shifted by an amount capital T. And this can further be written as the summation of each one of the deltas scaled by the corresponding value of x. So it'll become x of nt times each of the deltas that are shifted by nt. And we can draw this. We're still in the time domain. This will be our signal x sub s of t. And we just multiplied everything by this delta impulse train. And therefore, we just get deltas at these locations, at nt locations, that are going to be the height of x of t at that location. So that will look like something like this, where this is going to trace out, if we superimpose our continuous time signal on these things, it's going to trace out our continuous time signal here. So we can see that we have the same thing going through, something like that. But each one of these is at that height of x of t, and they are now going to be at these multiples of capital T. So t, 2t, 3t, and so on, and negative t, negative 2t in the other direction. So this is now a discrete signal. It is discrete because we don't know what happens to our actual signal in between each one of these deltas. All we know is what happens at the deltas, at these discrete locations, 0, t, 2t, and so on, at multiples of capital T. Now, in order to find the frequency content of a continuous time aperiodic signal, we use the continuous time Fourier transform. And I'm going to assume that we already know the form of that transform. And just to remind you, that's equal to the integral from negative infinity to infinity of x of t times e to the minus j omega t dt. This is a form of the continuous time Fourier transform. And so what we're going to do is we're going to plug in our discrete time signal into this formula to see what arises in order to get the discrete time Fourier transform. So we'll say that x sub s of j omega so the Fourier transform of x sub s of t, that's going to be the integral from negative infinity to infinity of x sub s of t e to the minus j omega t dt. And now we're just going to plug in what we just derived for x sub s of t. So that's going to be the summation from minus infinity to infinity of x of nt delta of t minus nt e to the minus j omega t dt. Now we're going to try to simplify things a little bit, and the first thing we see is that x of n capital T, well, that's not a function of lowercase t, so we can actually bring that out of the integral and put the integral inside because of the linearity of integration and summation. So we put the summation on the outside along with x of nt, followed by the integral of delta t minus nt, which is a function of little t, and e to the minus j omega little t, so we have to keep that in the integral. Well, using the same kind of properties that we did before when we showed that we can write this function up here as this one, basically that it's going to be just deltas scaled by the appropriate function value, we can do the same exact thing down here. So this part is going to be e to the minus j omega n capital T times delta of t minus n capital T, by the same kind of property that we had before, and therefore we can write our previous equation here from n equals negative infinity to infinity x of n capital T. And what we notice is that again we have a function here that's not a function of little t, and therefore we can bring it out as well. So that becomes e to the minus j omega n capital T times the integral from negative infinity to infinity of delta of t minus nt, because that is a function of little t, dt. Well, the integral of any delta is just going to be equal to 1. And therefore we can write this as the summation from negative infinity to infinity of x of nt e to the minus j omega n capital T. Without any loss of generality, we can let capital T equal 1. So we're saying we're just spacing things 1 apart, because we haven't really defined any time units, so we can just say that t is equal to 1. In which case, what we get is that x, and I'll explain this notation in just a moment, x of e to the j omega is equal to the sum from negative infinity to infinity of x, and here we're going to say that x of nt, well, that's equal to our sampled signal x of n, because it's just a function of n, capital T is fixed, times e to the minus j omega n, since capital T is equal to 1. And this is the final form of the discrete time Fourier transform, where x of e to the j omega is the discrete time Fourier transform, and this is how you get it. The reason that we changed the argument from j omega to e to the j omega is mostly to emphasize the periodicity that arises in the frequency domain. So before, for the continuous time Fourier transform, we just had a continuous frequency domain, and that's it. But now we've actually introduced a periodicity due to this integer value of n over here. And we can show this in a couple of ways. The first way that will show the periodicity in omega is just by plugging things into the definition of periodicity. In other words, we'll take e to the j omega plus an integer multiple of 2 pi and see what that's going to result in. That's going to be the sum from negative infinity to infinity of x of n e to the minus j omega plus k 2 pi. K is any integer times n. And this is equal to the summation x of n e to the minus j omega n e to the minus j 2 pi kn. Well, k times n is an integer, and e to the minus j 2 pi times any integer, well, that's equal to 1. So therefore, this whole thing is just equal to x of e to the j omega. And therefore, we've proven a 2 pi periodicity of the frequency spectrum. Another way to show the periodicity in a more pictorial way is to take the Fourier transform of x sub s, that sampled signal, and look at things in a slightly different form. So recall that x sub s of t, that's equal to x of t times this impulse train, which is going to sample our signal, just these deltas that are shifted. And if we take the Fourier transform of both sides, we can use the properties of Fourier transforms, and we know that multiplication in the time domain, as we have here x of t times this signal, well, that's equal to convolution in the frequency domain. So therefore, we have the convolution of the Fourier transforms of each of these individual signals. Now, just to get this in a nicer form, I'm going to let d of t equal our delta train function. So what we have then from here is that x of j omega, the Fourier transform of x of t, is being convolved with d of j omega, the Fourier transform of this delta train. Now, again, using the properties of Fourier transforms, you know that the convolution here is equal to 1 over 2 pi, negative infinity to infinity, x of j theta times d of j omega minus theta. So this is just the definition of the convolution. And furthermore, we know that d of j omega, we know its form. It's equal to 2 pi over t times the summation of k equals minus infinity to infinity of these deltas that are shifted now in frequency by integer multiples of 2 pi over t. Using this, we can rewrite our convolution as 1 over 2 pi integral of 2 pi over t from the d of j omega times x of j theta, and plugging in our actual form for d of j omega, we got that summation of the deltas shifted by integer multiples of 2 pi over t d theta. And without actually explicitly evaluating this integral, we know that the convolution of a signal and a delta function shifts the signal to the location of the delta function. Therefore, we know that this is just going to be the frequency response of x shifted to each one of these delta function locations. So that's just going to be all of the x's that are shifted to integer multiples of 2 pi over t. So in picture form, suppose now we're looking at the frequency domain as opposed to the time domain of our signal. So this is x of j omega, and maybe it looks something like this. So this is, again, just the continuous time Fourier transform of x of t, and it looks something like this. Additionally, we know that the Fourier transform of d is just again going to be these impulses that are going to be spaced at 2 pi over t apart. 2 pi over t and then 4 pi over t, and likewise in the negative side, and so on. And they have an amplitude of 2 pi over t. And then when we take the convolution of these two signals, our result is exactly what we have up here, and that's just going to be our original signal shifted to each one of these delta locations. And that's another way to show the same exact thing, that we now have this periodicity of the frequency spectrum. And again, without loss of generality, we can take capital T to be equal to 1, and therefore we see that we have this 2 pi periodicity if we take the Fourier transform of x sub s, which is equal to our x of e to the j omega, as we showed before. So this is just, again, another way to show why we get a resulting periodicity from the discretization of our time domain signal. The last thing I want to talk about is the intuition behind the discrete time Fourier transform. What we have is a discrete signal in the time domain. So for example, we have some discrete signal in the time domain. Maybe it looks something like this. And these are just these integer values, so 0, 1, 2, 3, -1, -2, and so on. So we have a signal that is completely discrete in time, which means that we know nothing about the values, because there are no values in between these locations. All we know is exactly at these locations, at 1, 2, 3, and so on. In the frequency domain, x of e to the j omega is a continuous periodic signal. So how do these two domains relate, since one is discrete and one is continuous? Well, the discrete time Fourier transform, that is x of e to the j omega, tells us how much of each frequency, omega, is present in our time domain signal x of n. It's beneficial here to look at the inverse discrete time Fourier transform, that is the synthesis equation, how to generate x of n out of our x of e to the j omega values. And this is one way to do this, and what this says is that we are taking the integral over a period of 2 pi of x of e to the j omega times e to the j omega n d omega. We only have to take a 2 pi interval for our integral, because x of e to the j omega is 2 pi periodic, and therefore all the information is contained in a single period of 2 pi. And what we're saying is that we're taking each value of this continuous spectrum and multiplying by the appropriate complex exponential or sinusoidal term that we use in our analysis. Basically, we are composing our signal x of n, we're creating our signal x of n out of this integration or infinite summation of these complex exponential terms that are scaled by their appropriate value x of e to the j omega. One way to look at this in the time domain is that each omega gives us a sinusoidal term. So it's going to give us some frequency. So for example, this is one of the omegas. And another one is at a slightly higher frequency, let's say. Something like that. And another one is going to be at yet a higher frequency. And so on. And we have an infinite number of frequencies, since x of e to the j omega is a continuous signal. So we have an infinite number of frequencies, and we add up or integrate all of their contributions, and at some particular time value, let's say at time value over here equal to 1, all of these contributions are going to add up to our original signal in the time domain, which was equal to this over here. And likewise, all the contributions at location 2, at time 2, are going to add up to exactly what we had for our time domain signal at that location. And so on. All of these contributions, these infinite contributions of the sine waves, are going to add up and create our original time domain signal from before, but only at these discrete values. Because x of n is a discrete time signal, we don't know or care what happens in between these sticks. Since x of e to the j omega is a continuous function, it uses these continuous complex exponentials. We have an infinite number of sinusoids, each one of which is a continuous function. Therefore, we do have values in between these samples. They don't have to go to 0. They don't have to be anything at all. As long as each of these contributions, they add up to the appropriate value at the location that we want, that's all that matters. And that's how we synthesize our signal back out of these discrete time Fourier coefficients or values. Likewise, what this equation over here is saying, this analysis equation, it's saying that to find the value of the discrete time Fourier transform at each frequency omega, we are going to multiply our signal values by some phase shifted version of this complex exponential. That's what this little n does. It creates this phase shift. So we know exactly at what phases and what amplitudes we need to have our sinusoids here, these x of e to the j omega values, in order to recreate our signal x of n. And this is exactly how the discrete time Fourier transform decomposes a discrete time signal into a summation or integration of cosines and sines, which then can be added back together to create our original signal at these sample locations. So basically, the discrete time Fourier transform finds the amplitude and phase, the information is contained in x of e to the j omega, for each frequency, which is in each individual omega, and there is an infinite number of them, to create the proper additions and cancellations at the proper locations to create x of n, only at the sample points. And it doesn't matter what's happening in between. Altogether, we have shown how to derive the discrete time Fourier transform in two ways and what the frequency domain is actually representing. We have also shown an intricacy of the discrete time Fourier transform, specifically its periodicity in the frequency domain, which comes about naturally from the discretization of the time domain. Finally, we discussed what the transform actually means and why it works.